Yeah. It's quite sound.
Está preparado, está preparado. ¿Podemos hablar directamente o ya está? No. Que no se oye aquí, ¿no? Solo se... No. Vale. Okay. Good morning, everyone. Thank you for attending this seminar. So it's for me a pleasure to introduce Professor Matt Visser. He's coming from University Victoria in New Zealand. And he was a student there. He graduated in both in mathematics and physics, and then he moved to US and he did a PhD in Berkeley University. After that, he has postdocs in University of Southern California and Los Alamos National Lab, and then he went to as a lecturer in University of Washington University in St. Louis. Place in which I have the chance and the good luck to meet him. So I did a postdoc with him back at the end of the 90s. And then from there, he decided at some point, he decided to come back to New Zealand, to his original place, as a full professor in mathematics. Well, he's still there. During all these years of career, he has been, he's very well known for at least two things, or maybe more. On the one side, he was one of the first people to start working on wormhole physics. And so he wrote a book that is a wonderful book that I can recommend to all of you, in which you can look at all the details of this fantastic physics in which you push the boundaries of general relativity to the limits. And then a few years after that, again, he found or he rediscovered something that has been discovered several times in the past century. Which is the subject he's going to tell us today about. This is analog space-times. And the nice thing is that once he started to work on this subject, when he was starting to do these things, nobody knew almost anything about that. But then I think he has been the major figure in making this, this subject something that now it has conferences, it has many people working on different, in theory, in observations. So for me, it's a pleasure to have him here. I think it's the person with which I have learned more physics in my life. So it's a pleasure to have you here. So whenever you want.
Okay, thank you, Carlos. Okay, as Carlos has given in that marvelous introduction, what I'm going to be doing today is to give a reasonably general colloquium level introduction to analog spacetimes, emphasizing why it is astronomers and physicists and mathematicians might all be interested in them for slightly different reasons. So the abstract that was circulated goes something like this. These analog spacetimes, they are ways of mimicking parts of general relativity. You're not going to get all of general relativity, but you're going to get enough to be interesting. And they're very, very useful for sometimes for teaching people mathematics, sometimes for letting people learn more about differential geometry, sometimes for letting people learn more about black holes and warped space-time and all that. The basic principle is, as long as you've got some background and perturbations running around on that background, as long as the perturbations have finite velocity, then you can set up some sort of propagation cone, like you would have a light cone in general relativity. And those propagation cones can be used in the mathematical sense to set up a conformal class of metrics on that region, and you can then really start to throw the mathematics of differential geometry at almost any system that has finite propagation excitations. If you are lucky, you can go further and actually turn it into a full-fledged Lorentzian metric and start to write down differential wave equations that look like curved space-time D'Alembertians on some background. And that background could be many different things, and I'm going to show you some examples throughout the talk of some of the backgrounds that are being used and some of the backgrounds that people are thinking about using. Sometimes you can use this to get a better idea of what's going on in general relativity. And sometimes you can use general relativity technology to turn around and look at these condensed matter systems or other systems and get a bit more insight as to what's going on in those systems. So, for example, I'll point you to this living review in relativity, and in fact that is by Carlos, Stefano Liberati from Italy, and myself. We're supposed to be revising it again since it's a living review, but it's already up to, last time I counted, I think there was over 700 references in the back of it, and it's about 150 pages long. So it's getting to the limits of what is going to be acceptable as a review. Okay, so let me talk a little bit now about emergent gravity, acoustic spacetimes, where I'm going to use sound in a flowing fluid to generate an effective spacetime. Surface wave spacetimes is when you look at ripples on the surface of some moving liquid. And again, you can throw some differential geometry at that and turn it into a statement about curved space D'Alembertians. You can do similar things with optics, with enough trouble moving a signal through a piece of optical glass can be modeled using differential geometry. Bose-Einstein condensates, metamaterials. The metamaterials is where all of the engineers are going, getting very enthusiastic right now. Have you heard of these people talking about cloaking devices? No? You will. Some of the actual engineers are seriously considering building cloaking devices. The bad news is that, sorry, their Romulan cloaking devices only work over a very narrow frequency range, and they're very useless outside of that narrow frequency range, but the ideas are out there. I'm going to actually wrap up a little bit by talking about the information puzzle in black hole evaporation, using the various techniques that I've got to then try and get a better grasp of what's going on there. Okay. So why are these analog spacetimes interesting? Well, what they do is they provide you with very specific, very concrete, very well-defined models for many of the individual things that go on in what we think of is eventually going to be quantum gravity or quantum gravity phenomenology. So that people thinking about quantum gravity think about black holes and Hawking evaporation. We can access that using this analog sort of technology. They think about things like breaking Lorentz invariance at ultra-high energy. We can model that using these sorts of analog spacetimes, etc. So the good news is you've actually got real experiments you can do in these analogs that you cannot do in general relativity, including, for instance, seeing Hawking radiation. Okay, we have seen Hawking radiation in analog spacetimes. We've not yet seen it in real general relativity spacetimes. Okay. The other thing is, you might have heard of people muttering about the word emergence and muttering that gravity is an emergent theory. Well, it's very hard to get a precise meaning of that word from the people in the GR community. On the other hand, in the fluid mechanics community, we've got a very concrete idea of what emergence is. We're trying to go from molecular dynamics at short distance to the Euler equations and continuity equations at large distance. Okay. Analog spacetimes already give you controlled models of Lorentz symmetry breaking. We can come up with a precise model where Lorentz symmetry is broken in a certain technically precise way, when you can actually do reliable calculations and understand the physics of what's going on. So I'm going to give a bit of an overview of all of these ideas over the next hour or so, and hope you come away with some sort of appreciation for what is going on here. Okay. This word emergence is thrown around very much in the GR, well, in the quantum gravity community specifically. But there's an awful lot of confusion of what it means. You may have heard of this famous article by Philip Anderson called More is Different, where he was basically arguing that in a condensed matter system, the sheer number of degrees of freedom means that there is a qualitative shift in what you're doing from few body systems. And his idea of emergence is simply that adding enough degrees of freedom to the problem is going to actually radically change the physics. People also talk about universality, and some of the people, when they talk about emergence, really are just doing something very basic like mean field theory. They're just saying, oh, I've got a complicated system, let me take some average and look at the fluctuations around that average, and maybe that's all I mean. So usage within the physics community is, in fact, I'm being polite here and I say not entirely consistent. The reality is the usage is completely inconsistent. So whenever you hear the word emergence, start digging to see exactly what this particular person is talking about, because the usage is all over the show. The safest thing you can say is that any time someone uses the phrase emergence, it means short distance physics is radically different from what's going on in long distance. Okay. The prime example of emergence is fluid dynamics, where your long distance physics is the Euler equation, the continuity equation, and some equation of state. Now, two of those equations are very generic. Euler and continuity equations, well, you better hope any models comes up with that. But the equation of state is very specific to the particular fluid you're working with. And that is the notion I also want to get across, that when I'm looking at these analog models, some features are very generic and map over very generically from one sort of system to the other. Other features can be very specific and don't map over in all that nice way. Okay. You cannot hope to derive quantum molecular dynamics by quantizing fluid dynamics. I've seen people try. It doesn't work. Basically because with molecular dynamics you've got fundamentally different degrees of freedom. You're dealing with atoms and molecules. There is no way you'll get that out of the continuum approximation. That hasn't stopped people from trying. It's just that the result has been an abject failure. So there has been a suggestion from the GR community that maybe trying to quantize gravity is the wrong thing to do. Maybe you should instead come up with some quantum system that has Einstein gravity as a low energy limit, but is in no sense a quantization of Einstein's general relativity. Now, it's easy to say that. It's very difficult to turn that into a very specific program. I mean, if you want to turn that into a specific program, there's two key questions you have to ask yourself. One is, can you somehow get space-time dropping out? And that's the generic question. And I'm going to hopefully convince you that getting space-time dropping out of these analog systems is not that hard. But the second thing is, can you get an analog for the Einstein equations? And that's the specific dirty question that requires much more direct knowledge of the intrinsic physics of whatever your analog model is. And that's kind of where things don't work so well. Okay. If Einstein gravity is emergent, then it makes no sense to quantize gravity, not as a fundamental theory. But that's a very big if, and people have been arguing about this for the last 25 years. If gravity is emergent, then the best you can hope for is some effective theory. That Uber theory, whatever it is, might not even be quantum. Gerhard 't Hooft has been arguing for the last 5 years that he can actually derive quantum mechanics from a classical theory. I'm not sure how many people believe him, but he's a Nobel Prize winner and he's doing serious calculations, so you should keep at least an eye on what he's doing. But on the other hand, whatever this theory is that we don't know what it is, it has to have in various limits classical Einstein gravity. It better be able in some other limit to give you non-relativistic quantum mechanics, because we know that works pretty well. It better give you non-relativistic quantum field theory of the sort that the, well, BCS superconductors, for instance, can be viewed as non-relativistic quantum field theory, complete with even the equivalent of a Higgs particle, which happens to be the Cooper pairs. You also better be able to get relativistic quantum field theory on flat Minkowski space, and you better get curve-based quantum field theory because, like it or not, we are living in a gently curved space in this room. And it's clear that quantum field theory is doing a good job of describing the standard model of particle physics. And you better get semi-classical quantum gravity. Now that's a lovely list of things to aim for. I'm not going to get anywhere near that. I'm instead going to argue that analog spacetimes are baby steps in all of these directions because they're showing you a way forward. Similarly, the string-inspired models, they're partially addressing all of these questions. Okay. And I think no one has a complete answer. The acoustic spacetimes are the first ones we ran across, at least the first ones I ran across. After we started digging through the history, we found traces of ideas going back almost to 1920. Okay, but the acoustic spacetimes are the actual easiest ones to think about, and I'll start for the mathematicians here with an actual theorem. Suppose I have a non-relativistic fluid, So because it's non-relativistic fluid, it better be described by the Euler equation plus the continuity equation. I'm going to assume the fluid is barotropic, which is a fancy way of saying that the density is a function of pressure, and I'm going to forget about entropy or anything like that. So density is a function of pressure only. Inviscid, zero viscosity. Irrotational, so that I can describe the fluid velocity by velocity potential. And then I'm going to look at linearized fluctuations on some background. The theorem then says that the linearized fluctuations, and if you're a classical physicist, you'll call them sound waves, and if you're a quantum physicist, you'll call them phonons. Well, those linearized fluctuations are described by a massless, minimally coupled scalar field in 3+1 dimensional space-time that is described by a metric that has nothing to do with general relativity. It's a metric that has to do with the density of fluid, the speed of sound, and the velocity of the background fluid flow. And this is actually a rigorous theorem of mathematical physics, which copies over things you would have only seen most likely in the context of general relativity into now a context of looking at fluid flow and looking at linearized perturbations on the fluid flow. Notice I'm not saying this metric satisfies the Einstein equations. This metric is given by the background density, the speed of sound, and the speed of the fluid. So this background metric actually is governed by the Euler equations and the continuity equations. So what you do not get here is the Einstein equations. You just get half of general relativity, which is whatever depends on curved spacetime, whatever depends on putting a particle in the curved spacetime, you can get out of this. But you can't get the Einstein equations itself. I can calculate, of course, the Einstein tensor and the Ricci tensor, but I've never been able to turn the Einstein tensor or Ricci tensor of this metric into anything that has a natural interpretation in terms of questions that fluid mechanics people would ask. Now, I'm not going to bore you with the proof of this. I will point out a couple of other simple things. You can play the simple game of inverting the metric, okay, to find the metric with its indices up. The worst you have to do is invert a 4x4 matrix. Better yet, take this, compare it with the other one, multiply the two out, and you can check that you get the Kronecker delta. If you want to use the sort of language you'll most often see in relativity, ds squared equals gab dxa dxb, well, you can certainly write it this way. ds squared is now minus speed of sound squared times dt squared, where remember in Lorentzian, say in Minkowski space, you would just have c squared there, the speed of light. And instead of dx squared, I have dx minus v dt. And the v is there just because there's some background fluid flow. If the background fluid flow was 0, I just have minus dt squared plus dx squared, and you'd see, ooh, it looks like Minkowski space, except I've got the speed of sound sitting there. And I've got that nasty prefactor, the density over the speed of sound. And the only reason I need that is to actually get a nice minimally coupled D'Alembert equation. If I'm working in the ray optics limit, okay, in the ray optics limit you don't try and solve differential equations, you just look at geodesics for rays. Well, then I can just ignore the prefactor. You've probably all seen in general relativity that photon trajectories are independent of the conformal factor, so I can always forget the conformal factor if I'm trying to find what a photon is doing in general relativity. Same thing here, a phonon in this model doesn't care about the conformal factor. You just want to look at ds squared equals 0. And what does the condition ds squared equals 0 correspond to? Well, it corresponds to having sound cones rather than light cones. And if I look at a particular point as the fluid is moving past, then this spherical shell has been swept along by the flow. This one was emitted 2 seconds ago, say it's been swept along further, this 3 seconds ago, and so on. So what you have in this situation is that if you move with the fluid, the null cones spread out at the speed of sound. If you try to stand still, the null cones, the sound cones, propagate anisotropically. And the anisotropy is governed exactly by the speed of the fluid flow. Of course, the crazy thing is you can even get acoustic horizons if the fluid speed goes supersonic. Because once the fluid speed goes supersonic, your sound cones are tipped over so far that you cannot head straight up anymore. You are being swept along by the fluid flow. Now, I'll give you 3 examples of this, 2 of them actually from astronomy. Some of you may have heard of Bondi-Hoyle accretion onto a dark object. This is when you have some interstellar medium spherically, symmetrically accreting onto some dark object, some dark compact object. You look at this interstellar medium, it falls down basically under Newtonian gravity and the free fall. Eventually, the infall speed exceeds the speed of sound in the fluid. And even in Bondi-Hoyle accretion, you have a, honest to God, acoustic horizon forming. And people have looked for these things, and from what I can tell, though I'm not an expert on that part of observational astronomy, they've seen it. The one you may have not have heard of is that the solar wind is an example of this. And in fact, the sun is an acoustic white hole. Because the solar wind, as it boils off the sun, somewhere near the edge of the photosphere, it goes supersonic. And the solar wind remains supersonic until somewhere near the orbit of Neptune, near the heliopause. So in that entire region between the photosphere and the heliopause somewhere out near Neptune, if you look at sound waves propagating in the solar wind, those sound waves propagating in the solar wind behave as though they were in a white hole space-time rather than a black hole space-time. This has actually been used in particular to argue why it is that the photosphere is stable, because if you get outside perturbations trying to get back into the sun to destabilize the photon sphere, well, unfortunately, the flow is supersonic. They're going to get turned around. They're not going to actually make it back into the sun to destabilize the photosphere. How many people have heard of a Delaval nozzle? No one. The Delaval nozzle is a cute one. It's a nozzle that is carefully designed to, just concentrate flow down, and of course, here you just put in some stuff at subsonic speeds, and of course you know what happens. The nozzle squeezes things down so the velocity goes up. If you do things just right, you can get the flow to go supersonic exactly at the throat of that nozzle. And care to guess what happens downstream when the nozzle widens up again? It speeds up. It doesn't slow down. Okay, so your normal intuition that when you focus a fluid flow down, it speeds up. Yes, that works in the subsonic regime, but it fails in the supersonic regime. You can get an acoustic horizon here, and then a supersonic flow downstream. And here the equations are simple enough that I'll spend just a couple of minutes to throw this at you, because it really just boils down to playing with the continuity equation plus the Euler equation. The continuity equation just tells you the density of fluid times the velocity times the cross-sectional area is a constant. Okay. That's just conservation of mass. The Euler equation relates the density times the acceleration to the gradient in the pressure. But the acceleration is just v times dv dx, so vv prime. And the gradient in the pressure, well, remember I said barotropic, so I'm forgetting entropies and all this. I'm just saying then dp dx is dp d rho dx, but dp d rho is just the speed of sound squared. So you have a formula relating density, velocity, velocity gradient to speed of sound, density gradient. Eliminate the density between these two, and that's not a big deal because you can differentiate this one to relate rho prime to a prime. You can eliminate then rho on both sides. You get, after just a few seconds work, a relation between the velocity gradient and the rate of change of the cross-sectional area. And there's this lovely factor out here of speed of sound squared minus velocity of fluid squared. And when that goes through zero, which is when the flow goes supersonic, you suddenly get a sine flow. In fact, let me introduce the Mach number, which is just v divided by the speed of sound. If I divide this by the speed of sound, I get 1 minus the Mach number squared times v prime over v equals minus a prime over a. As long as the Mach number is less than 1, a decrease in area leads to an increase in velocity. As soon as the Mach number goes over 1, you reverse this. Okay. So that is enough to tell you that in these de Laval nozzles, if you have an acoustic horizon, it has to be at the narrowest point of the throat, because the acoustic horizon corresponds to Mach number 1, which means a prime over a is 0, which means a prime is 0. It has to be at the narrowest point. Then if you put two de Laval nozzles in a row, if the flow is supersonic here and you squeeze it down, it does slow down, contrary to what you expect. And you'll get a second acoustic horizon here before you then have subsonic flow at the back end of the de Laval nozzle. Okay. So here is an example of an acoustic space-time where if you wanted, you could avoid all of the comments of differential geometry. But if you don't, I can write down an effective space-time metric that governs what's going on in this particular physical setup. Okay. So let's get a little bit fancier and not talk about de Laval nozzles again. I'll talk about generic acoustic spacetimes. And I'm going to play a minor trick. I'm going to try and define not the Mach number, but the normal Mach number to a surface. Because the velocity is a vector. And if you want to know whether or not a signal can escape or not escape, you want to look at a particular surface and ask, what is the velocity perpendicular to that surface, and how does it compare to the speed of sound? So I'm taking the velocity of fluid, taking its dot product with the normal to the surface, so I'm finding the normal component of the velocity, dividing by the speed of sound, and when that normal Mach number is 1, you can never get an acoustic signal back out again, so this is a acoustic apparent / trapping horizon. And here I'm actually making a distinction between apparent horizons and event horizons, because strictly speaking, the notion of event horizon makes absolutely no sense in this acoustic model, because I could just take my experimental apparatus and turn off the pump and let the fluid flow go back to 0, the horizon's going to disappear. Okay. The technical definition of an event horizon requires it to exist forever into the future. These particular horizons, they come into being once you set up the supersonic flow. They're going to disappear as soon as you turn off the supersonic flow, and therefore these are going to be what the GR community calls apparent horizons, or if you've been a little fancy, you call them a trapping horizon. Now, often this distinction has not made it into the wider community, and that's unfortunate, because event horizons are very good for proving mathematical theorems, but there's also an equally good theorem that says that no experimental physicist can ever detect the presence or absence of an event horizon, simply because with finite resources, to know that there's an event horizon, you have to wait until the end of the universe and backtrack from the end of the universe to figure out what was the last photon that escaped. Okay? No one can ever do that. Whereas apparent horizons and trapping horizons, at least in situations of high symmetry, are much better behaved. And so you can really think of someone who's got a finite sized laboratory and taking data for a finite amount of time. They have a fighting chance of detecting apparent or trapping horizons, but they've really got no way of getting honest to God of getting honest to God event horizons. Okay, you can copy your favourite stuff out of your general relativity book and calculate the surface gravity of this acoustic horizon. And it's remarkably similar to what happens to the surface gravity of a general relativity black hole. You're actually looking at the horizon, and effectively in this case it turns out you wind up looking at the velocity of the fluid as it crosses the acoustic horizon and finding its acceleration, and this turns out to be identical to the surface gravity. In fact, all you need to do is find the speed of sound at the horizon. You want to find your normal Mach number, which is 1, but you look at its gradient as it crosses the horizon and find its absolute value. There is a calculation required to actually convince you that this is completely equivalent to the way surface gravity is defined in your favourite general relativity book, but it is. We spent a lot of time setting it up and making sure. And this is the killer. Hawking's calculation for the evaporation of a black hole carries over to these acoustic horizons. And way back in 1981, Bill Unruh already noted something pretty much like this, and he said, yes, these acoustic horizons are going to generate phonons with a Hawking temperature that is related to now the surface gravity, which is related to the acceleration of the fluid as it crosses the acoustic horizon. And now the question is, do we have any hope of finding these phonons as opposed to finding the photons? Okay, for a real general relativity black hole that starts from stellar collapse, okay, 2 or 3 times the mass of the sun, you can calculate the Hawking temperature and it's nanokelvins. Now, unfortunately, you've got a 2.8 Kelvin background coming from the cosmic microwaves, so trying to detect a nanokelvin perturbation on a 2.7 Kelvin background, forget it. You're not going to see it. Whereas here, you've got a whole different game where you can start trying to think about, are there situations under which we might possibly be able to detect Hawking radiation from an acoustic horizon? The first obvious thing is, you know, put some water pipes in the laboratory, and then you go, well, wait a minute, I would need the water in these pipes to be moving at 1 kilometre per second. The safety people are probably not going to be too happy with you having pipes full of water moving at kilometres per second. No, that's not going to happen. But there are other things that can be done. Okay. But before I get on to the experimental situation, I'll talk a little bit more about some of the other things you can do. What I talked about there was completely non-relativistic. You can do something general relativistic. You know, you can start with an ordinary general relativity background. On that, put some moving fluid, and you can ask what happens to the perturbations on that moving fluid in a general relativity background, and you'll get a formula that some of you might recognise because it's become reasonably popular now. It basically says you look at your usual metric, you find the fall velocity of fluid V, you go to the rest frame of the fluid, You throw away the corresponding -1 in the space-time metric, and you replace it with minus speed of sound squared. And there you have a metric that describes sound cones in a completely relativistic manner. There's a reason I don't show you what this conformal factor is. It is a quite horrible mess involving the enthalpy and the energy density and the baryon number density of the fluid, so it's quite nasty. Physicists now call this the disformal transformation. If you just had this, it would be a conformal transformation. You add this to it, it's called disformal. And after we went to the trouble of writing this down, we went and dug back deeply enough. And yes, this was first written down without the conformal factor by Gordon somewhere around 1920. And yes, this is the Gordon of the Klein-Gordon equation. And what he thought about in the question of back in the 1920s is what happens if I now try and do special relativity, but I have a medium which has a refractive index. Okay, so my medium has a 4 velocity and it has a refractive index, so the light cones are going to be different. What do? I take Minkowski space metric, I get rid of the -1 by this, and I replace it by the effective speed of light that depends on the refractive index. And so this metric was already there back in about 1920, and then quietly ignored for a very long time until people started getting interested in these things again back in the 1990s. If you add vorticity, it's much messier, and I'll just throw you two horrifyingly complicated equations which will require quite a bit of unpacking in terms of translating out of lovely index-free geometric notation that the mathematicians love to try to convert this into a physics. Okay, so the only message to take is if you've got background vorticity, things get very messy. Okay. In this ray acoustic limit, ray acoustics means you're only looking at paths of perturbations, you're not trying to solve wave equations, then I never care about the conformal factor, and all you need to know is the speed of which the propagations move and the background speed of the medium, and you're going to get that thing immediately. We can try to generalize this. So-called rainbow geometries are when the speed of sound depends on frequency. Or when the okay. And people have tried. This is one way you can break Lorentz invariance, by letting your propagation speed become frequency dependent. People have looked, and as far as we can tell, in general relativity, this is not happening. So, to the best of our knowledge, the propagation speed really is c, the low energy speed of light for all known velocities. But here at least we have a coherent framework for how to address questions of possible Lorentz violation in an internally consistent manner. It's very easy if you just randomly start with the Lorentz transformation and start, you know, modifying bits and breaking bits and pieces, you can easily get inconsistency. This is guaranteed to be consistent because you're starting with a very concrete physical model. You can play the same thing with surface waves. The main difference with surface waves is you don't talk about the Mach number, you talk about the Froude number. Okay, the Froude number is the ratio of the speed of the surface fluid to the speed of the ripples that move around on it. And of course the speed of the ripples is governed by different physics from the speed of sound waves going through the bulk. And again, once we dug deeply enough, we found that the fluid mechanics people had been thinking along these lines a long time ago, but they'd never phrased it in the language of differential geometry. The fluid mechanics people talked about something they called wave blocking, which happens at Froude number 1, which means that the ripples can't find their way upstream anymore. And these days, we at least use the phrase blocking horizons. Blocking horizons are where the Froude number exceeds 1, where suddenly you can't seem to ripple upstream anymore. So here I've got a lovely example from a weir, which is very closely related to a hydraulic jump. You can pretty much see the reason this is so smooth here is there's no way the ripples can fight their way back upstream against a fluid flow. You've definitely got a Froude number exceeding 1 here. This is a real photograph. This is a real photograph. Anyone care to guess what you're looking at there? It is actually from Monticello, California, and the engineers were having a lot of fun. This is a water reservoir, and they deliberately made the overflow pipe a vertical pipe that stuck up to just below the surface of the water. So this actually is the overflow from the reservoir. This pipe goes down and is how the reservoir doesn't actually completely flow up. This actually is a little line of buoys, and the idea is to stop the kayakers from getting too close. Okay, I have heard rumours that one guy actually tried it and survived. Again, you'll see how smooth this is here, and the smoothness again is a reflection of the fact that the ripples cannot fight their way back upstream anymore because the Froude number is exceeding 1. Now, here's a good thing for teaching purposes. If you really want to convince someone that there's a difference between an ergo surface and a horizon, think of a draining bathtub. You all know you pull the plug, the water starts swirling, and so on. Now, there are two interesting surfaces if I have a draining bathtub with the water swirling around like this. One of these red surfaces is when the speed of the fluid exceeds the speed of the ripples. Now, if the speed of the fluid exceeds the speed of the ripples, this means the Froude number is bigger than 1. It means I cannot send a ripple back up in this direction. On the other hand, I might be able to send a ripple off to the side and it would still escape. The second red surface is where the normal Froude number exceeds 1, which means that the normal component of velocity, the radial component of velocity, exceeds the speed of the ripples. At that stage, nothing is going to escape. So this one is a horizon, this one is less than a horizon, it's an ergo surface. Try it and see what happens if you head off to this direction. You just barely manage to escape. Okay, looking at the time, let me actually start to wrap up. I'll say yes, we can define normal Froude number, go through the same calculation, and we should see a Hawking radiation of riptons with a temperature that's given by the acceleration of the fluid as it crosses through this ripple horizon. Good news is, look at this thing, h bar omega over kBth. Once you actually put the h bars into the Hawking temperature and the kb's, you find that this thing is actually independent of h bar. It just depends on things like the frequency of the wave, the speed of the surface, and the normal derivative of the Froude number. So this is completely classical. So the object that shows up here, if you divide this by, if you compare this to h bar omega, do the division, you find you get something completely classical. So there is a classical limit for Hawking radiation, and this classical limit, in particular the classical limit of stimulated Hawking radiation, has already been observationally probed in the laboratory. Okay, these experiments have been done, the effect is there. And here I'm referring to the work by Silke Weinfurtner, Ted Tedford, Matthew Pence, Bill Unruh, and Greg Lawrence, who published a paper that's now 6 years old now, where they looked at a measurement of stimulated classical limit of Hawking emission in an analog system. And they were looking actually at something like, whoops, not optical, they were actually looking at something like this. They actually had a wave tank, and they set up a fluid flow in the wave tank. They sent waves upstream that bounced off the blocking horizon and stimulated a more stuff coming back that went in, and that can be interpreted as a Hawking-like process, and they have measured the Boltzmann factor. They could not see the peak in the Planck spectrum, so they couldn't tell the difference between fermions, bosons, Boltzmann, Bose, Fermi statistics. But the fact that they could at least in the tail see that there was a Boltzmann factor, and they couldn't calculate this ab initio, but they could find a fit it to the data and say, yep, take logarithms, it's looking pretty exponential, it's good. Bill Unruh has now for a long time been arguing that yes, this means Hawking radiation has been measured, analog Hawking radiation, not general relativity Hawking radiation, but all of the relevant details that go into Hawking's calculation wind up being copied into this calculation as well. So it's something that gives us a lot more confidence that Hawking radiation from black holes actually exists. People have also worked around with optical spacetimes. Now let me first give you the theorist toys. If I've got a refractive index that depends on position, I can reinterpret that as a 3x3 metric that's conformally flat, and everything you know about the propagation of light rays in a position-dependent refractive index can be mapped into a statement about geodesics in a conformally flat three-dimensional geometry. Okay, so physicists love this, mathematicians love that. A slightly scarier one is everyone's heard of Snell's law. What's less obvious is that Snell's law is related to the existence of killing vectors and tangent vectors. How many of you have seen the statement that if you've got a killing vector in the space-time, it leads to a conservation law because the tangent to a world line contracted with the killing vector is a constant? No? Conservation of energy, conservation of angular momentum in Schwarzschild. A particle, if you drop a particle in a Schwarzschild space-time, there's still a conserved quantity, the energy of the particle. There's a conserved angular momentum. It turns out you can rephrase Snell's law in this differential geometric way as a statement about killing vectors and symmetries and conserved quantities. But now the experimentalists, well, what have the experimentalists been up to? They have been trying to get Hawking radiation from laser pulse filaments. And let me just show you roughly what's going on. You have an input beam, you go through a piece of optical glass, and they do see photons coming out. The good news is this is actually photons rather than classical waves, so it's clear they're seeing something that's quantum. The bad news is that you'll see from the diagram that these photons are coming out at 90 degrees. So if the horizon is doing this, the photons are somehow coming out like this. And I would not have expected that. If I've got my horizon here, I would expect the Hawking photons to be coming out here. So it's not entirely clear what's going on there, and there's still some kinematic controversy. The other controversy, I talked to one of the experimentalists, and they told me that they drive this process at such a high energy that they can actually hear the crystal cracking as it's being driven beyond all its elastic limits. Okay, and if you've ever heard of something called triboluminescence, you will know that if you take a crystal and crack it, you do generate photons in the visible regime. So there's a number of reasons for being just a little queasy, and there is work going on, however, into trying to deal with these issues and trying to redo it. The last one I'll talk about is the Bose-Einstein Condensates. And the Bose-Einstein Condensates are great because, first, the speed of sound in a Bose-Einstein condensate is very low. It's a few millimeters per second. Second, it's very easy to get Bose-Einstein condensates flowing at millimeters per second speeds. Basically, all you need to do is take a laser and stir it, quite literally. So as of 3 years ago, Jeff Steinhauer from Tel Aviv was claiming, quote, "We thus observe self-amplifying Hawking radiation." Okay, so again, this is an analog system. Speed of sound is about a millimeter per second. The Hawking radiation is higher than the temperature to get the condensate, so you've got a hope of getting a signal. People have been gearing up for this whole thing for over a decade, and I would say at this stage it's almost certain that one way or another we've seen Hawking radiation. Metamaterials. Metamaterials are fascinating. Looking at the time, let me just skip through and I'll say what's happening now with the metamaterials is people are deliberately engineering, using small circuit resonators, active elements that are effectively allowing them to tune the permittivity and permeability arbitrarily. And as long as permeability equals permittivity, this is not exactly the obvious thing you would have thought of, but as long as permeability equals permittivity, then you can actually factorize the, okay, what shall we call it, the impedance tensor that relates E and B to H and D. That factorizes into a pair of products of effective metrics. So under certain circumstances, if I take a material with permittivity and permeability, I can rewrite the propagation as though it was propagation in an effective metric. And once we did enough digging, we found this was actually an exercise in Landau and Lifshitz. Okay. In a limited sense. Okay, Landau and Lifshitz only looked at a particular simplified case, and we have managed to extend what they were doing quite radically. But already from the Landau and Lifshitz exercise, you find that if you want to get a honest-to-God effective metric and nothing else, then you have to impose permittivity equals permeability. Okay, where am I? I think I better, actually I'll skip this bit. I'll just say the annoying bit with the analog program is it's distressingly easy to get multi-refringence as opposed to just simple light cones. Okay, birefringence you will have heard of in the wrong sort of crystals. If you've got a whole collection of systems interacting with each other in some complicated way, it won't just be birefringence, it'll be multi-refringence. And that gives you extra structure, none of which we've seen in general relativity or the real world. So we do have to be cautious with the metamaterial models we build or with the analog spacetimes we build, that we're not introducing extra stuff that doesn't actually reproduce what we see in reality. In view of the time, well, yeah, it is more than just light cones. You do actually have to look at wave equations. In view of the time, I don't think I'll talk about this, and I'll just conclude. There's a lot of very interesting work going on with these analog spacetimes. We don't have the Einstein equations coming out of this, but we see some hints about maybe doing something along those lines. There's a number of experiments that have already been done and are actually quite effective. I mean, most recently, Silke has a lab up in Nottingham where she has actually got vortices running and has actually been able to measure superradiance in the laboratory. So it's not just a theoretical phenomenon anymore. Superradiance from vortices has now been experimentally detected. And finally, I'll say there's some very interesting matters of principle to consider. And at that stage, I'll say thank you.
Hi, just the tiniest, silliest little question. In terms of the cloaking devices, what kind of frequency range are we talking about?
I think the experimentalists have been playing in the microwave region.
Okay.
Okay. Well, you're looking at RC circuits. There's no way to get a RC circuit that's, that has a resonant frequency in the optical.
Yeah, it was exactly the question.
Yeah.
How wide is that, do you know?
Oh, I better not say. You should probably look up some papers by Pendry and people from within the transformation optics community.
No worries.
Okay. But I think it's wide enough to be potentially of interest for the military. Well, they just want cloaking against radar. I mean, and camouflage paint will take care of the cloaking against visible detection.
In fact, it's very funny that
when one of the main tools and one of the most important things in general relativity is this general covariance. Means that you can write down things in whatever coordinate system that you want, and everything seems the same. So in these metamaterials, is precisely you use this fact to transfer a property that you want to a system in which this is portrayed in a deformed way. So these devices are being assisted by the general relativity techniques.
Effectively, this thing they call transformation optics, or the transformation method, basically boils down to, here is something interesting. Let's put some random coordinate transformation on it to try and see what this would look like if I tried to build it in the laboratory.
Some additional questions? Okay, if not, let's thank Matt again.